Hello everybody and welcome back. We're going to shift our attention now to dose in CT imaging. And I want to separate this into three different modules. The first, being today's talk, we're going to look at what exactly dose is and how dose is imparted on tissues. We're also going to look at some of the basic units we use to describe dose. Then we're going to look at dose specifically in CT imaging, how we go about estimating the amount of dose a patient receives during a specific CT examination, and how we can use that dose estimate to try and figure out the long-term stochastic risk for that patient, say of developing cancer, for that specific examination. Finally, we're going to end off by looking at the factors that influence dose. What can we change as radiographers or radiologists to increase or reduce the amount of dose that a patient receives during a CT scan? I feel like one of the common issues that people have when they first start learning about dose in CT imaging is the sheer amount of different terms, or the sheer number of different terms that describe dose in imaging. Now, each one of these terms represents something slightly subtly different from the other. And hopefully by the end of these three modules, we will have detangled this mess. We'll have gone through each one of these terms and we'll know exactly what they represent and most importantly, what they mean for the patient. Now, I think the best place to start is to define what exactly dose is. Now, whenever you see a dose estimate or a dose figure, it's describing one of two things. Either it's describing the amount of energy that's deposited in the tissues of that patient. We measure that using the units gray. Or it's determining the stochastic risk to that patient from the dose that they've received. What's the long-term likelihood that they're going to develop something like cancer in the future based on the ionizing radiation that they've received here? Grays talk about energy deposition, sieverts talk about risk estimation. Now that's the units that we use to describe dose, but how does a patient actually receive dose? Well, in CT imaging, we're talking about X-rays, and we know that X-rays can interact with matter in one of three ways. They can either be transmitted through the patient, they don't interact with the tissues at all. They can be attenuated by the tissues in the patient through the photoelectric effect, or they can be scattered via Compton scatter or Rayleigh scatter. And it's the attenuation or scattering that causes energy to be deposited in the tissues and ultimately leads to ionization of atoms within the patient here, which is what dose is in the patient. So let's look at these two processes in more detail. First, we'll start with attenuation or the photoelectric effect. We have our average atom here within the patient, and we have an incident X-ray photon interacting with this atom, and it's going to eject an electron from that atom. It's ionizing this atom here. We get the ejection of a photoelectron here, and this X-ray is causing ionization of this atom. So one X-ray is going to ionize one atom here and eject a photoelectron. It's this photoelectron that's actually going to impart most of the dose on the patient. This initial ionization is a very small part of the dose. In scattered radiation, again, we have an atom, and we've got an incident X-ray that is not fully absorbed by the electron that it collides with. The electron is released, this is a Compton electron or a photoelectron that's released into the local tissues, as well as this scattered X-ray that deflects at a certain scatter angle here. This X-ray can then go on to ionize further atoms as well. But this ionization based on the electromagnetic radiation, importantly, is a very small part of the dose. This electron is going to impart dose. So let's follow this electron and see what it does as it passes through local tissues nearby to where that interaction occurred. If we think of the tissues surrounding as having multiple different electrons, this is very much a diagrammatic representation. All these electrons are part of different atoms, part of different structures here. The initial ionization event from the electromagnetic radiation or the X-ray photon occurs here. That photoelectron is then going to travel through tissues. It's going to move in a non-linear line because it's going to be repelled by other electrons. Negative charges repel each other. Not only that, it's going to slow down, as you would have seen from that animation, as it comes to rest here. It starts off with high kinetic energy, gets lower and lower kinetic energy as it comes to rest, as it travels along this path here. Whilst it's traveling through the tissues, this is the most important part, it's going to repel surrounding electrons along that path. It's that electrostatic force of repulsion that's going to ionize different atoms along this path here. That's the major energy deposition that's going to happen in tissues. That's the major dose that's imparted on this patient. It's not that initial X-ray. The electron moving through these tissues and imparting energy into the tissues or ionizing surrounding atoms is what's known as linear energy transfer. We are transferring energy, that kinetic energy from that electron. As it slows down, it's transferring energy out into the tissues. Now, I don't know if you've seen these ramps here before. We have many of them here in South Africa, where there's a long downhill, say, coming down off a mountain pass. And if a truck was to lose its brakes, instead of continuing along the road, it would divert its path and would go into this pit here that's filled with sand and rocks. Linear energy transfer is very much dependent on the type of vehicle that's traveling through the tissues. In CT examinations, we're dealing with electrons that are traveling through the tissues, light, very small charged particles. When we go into our nuclear medicine block, we're going to look at much heavier, much more highly charged particles like alpha particles. We can think of an alpha particle as being a large, heavy truck that's traveling into the sandpit. The rocks and the sand in this sandpit here are not going to divert the truck very much. The truck's going to take a pretty straight path. It's going to displace a lot of sand, impart a lot of dose into the sand here, and it's going to travel a very short distance before coming to a halt as it buries into the sand there. If you think of an electron traveling at the same speed, but an electron is someone on a bicycle, as they hit the sandpit, they can be bounced around a lot. Each rock is going to cause that bicycle to change path. It's not going to displace much sand, and it's going to travel a much further distance through these tissues. That's similar to what linear energy transfer is describing, and it's very much dependent on the type of particle that travels through the tissue. And it's important to remember that it's electrons, photoelectrons that have been ejected from atoms that are imparting dose into those tissues in CT imaging. So that's all good and well, but where is that electromagnetic, that ionizing radiation coming from? Now, when we're talking about dose, that source of ionizing radiation is what's known as the emission source. Now, either the source can be from a radioactive substance that we're going to look at when we go into our nuclear medicine learning pathway, where we have an unstable atomic nucleus that's going to decay and release ionizing radiation. That's not the case in CT imaging. We know that X-rays are released from the anode in our X-ray tube that's rotating around the patient. And emission of those X-rays occurs at the focal spot where we're generating X-rays through the characteristic and Bremsstrahlung interactions here. And those X-rays are going to be released at multiple different energies based on the energy of the electrons being accelerated towards the anode and based on the material that the anode's made out of. And the number of electrons is going to differ depending on the current that we're passing through the filament, as well as the tube potential here. And the number and average energy of those X-rays is what's known as the photon fluence. Now, emission of X-rays doesn't mean that they are going to impart dose. They have to interact with tissues for dose to occur. If you have a radioactive substance that's in the middle of the ocean and no one's near that substance, we're not being exposed to that radioactivity. There's a difference between emission, actually releasing ionizing radiation, and exposure. When we talk about exposure, we talk about the interaction between emitted ionizing radiation and some form of tissue. Here we've got a tube that's filled with air. X-rays are heading towards that tube, going to interact with atoms within the air there. Some of them are going to be transmitted without interacting through this chamber, and some of them are going to interact with atoms and release electrons. This interaction here, this release of electrons, is what's known as exposure. It's the interaction between ionizing radiation and matter. Now, how do we go about measuring exposure? This is ultimately what we want to eventually measure in our patient that's getting a CT examination. What we can do is place electrodes on either side of this gas chamber that's filled with air. You can run a wire between the two and put a voltmeter here. If we were to make a charge differential between these electrodes, what's going to happen is those electrons that have been released are going to flow through the tube and ultimately change our voltmeter here. Look what happens to the voltmeter here as we pass a charge through here. The volts that pass through this wire are going to be proportional to the number of electrons that have been released by this ionizing radiation. And we can measure exposure here by calculating the amount of charge that's been released over the mass of tissue or the mass of the chamber that we have here. That charge we're going to measure in coulombs, the mass we're going to measure in kilograms. This is coulombs per kilogram. The other unit you may have heard of this is called a Röntgen. Now remember, when we're talking about dose, we're either talking about energy deposited into tissues or we're talking about risk to the patient. Now air has no risk here. We're not calculating any risk here. The air is not at risk of getting cancer. What we almost calculating here is energy deposited into tissues, but we haven't actually got energy here. We've got charge deposited into tissues. we can convert this exposure value into an energy per kilogram value using something that's known as KERMA, kinetic energy released per unit mass. And because we're dealing with air here, we can calculate air KERMA. We can take the exposure that we've just calculated here with our electrodes, and we can multiply that by the average energy it takes to release an electron from an atom in air, divided by the charge of an electron. This charge of an electron is going to cancel out the coulombs here, and we're going to get joules per kilogram as our unit. Air KERMA is measured in joules per kilogram, and that joules per kilogram is what's known as a gray here. Now we can measure at least the initial energy that's been deposited by this emitted X-rays being exposed to this air here. Now, air KERMA is not the same as tissue KERMA. We know that the average energy to release an electron in air is going to be different from that in tissues. What we want to calculate is the dose in tissues, not the dose in air. And that dose in tissues is what's known as the absorbed dose, also measured in grays. We normally measure it in milligrays. Now, the problem is we can't put electrodes on either side of our patient and have the patient sitting there with tissue and measure the charge running through the patient. That's completely impractical. We still measure this absorbed dose, a dose in tissue, by joules per kilogram, but we don't actually have a good way in a CT examination to say this is the exact absorbed dose that this patient is getting. What we end up having to do is estimate dose. And you'll see that trying to calculate or at least estimate absorbed dose is fraught. It's very difficult to get an accurate measurement of this. And this is one of the major issues when it comes to dealing with dose in CT imaging. Firstly, if we were to place this patient in a CT machine, we know that dose, as X-rays pass through this patient, is unevenly distributed. X-rays get attenuated as they pass through the patient. Now, we're looking at this side on. If we look at the patient end on, we can see the X-rays passing through the different regions of the patient, and they pass through different lengths. Their attenuation, their linear attenuation, is going to occur differently depending on how much tissue they pass through. Now, that dose is unevenly distributed. Not only that, but the CT machine is going to rotate around the patient, and you'll see how dose then is distributed in a typical single slice in a CT examination. We get a lot of dose on the peripheries of the patient with less dose in the middle. So you can see that this is our first major challenge when it comes to estimating dose within a patient. We get an unequal distribution of dose here. Not only that, but the size of the patient is very important. Let's take that same CT examination, but we're going to reduce the size of the patient. The same current going through the filament, the same tube potential, all the parameters are the same. But now we can see that this smaller patient is going to receive a much higher absorbed dose per kilogram of tissue. We compare these two patients here. These two patients within the same CT machine, but look how much more dose this smaller patient, say a pediatric patient, is going to get. So it's difficult to plug in certain parameters on a CT machine, not take into account our patient that's sitting in there and try and figure out what dose they're going to be. We can't standardize absorbed dose. We need to take the patient into account. So you can see it's difficult. We can't directly measure absorbed dose. We can't measure it for multiple different reasons. I've mentioned some of them. We see that energy deposition differs depending on the tissue type. The same exposure of a certain X-ray fluence to, say, bone and lung is going to result in very different energy depositions. Most of the X-rays pass through lung. They're transmitted through lung. Most of the X-rays are absorbed by bone. So the same X-ray fluence is going to cause much more energy deposition in bone than it does in lung. Our absorbed dose is going to be different between those two tissues. We know that energy deposition is not uniform, especially once we start to account for the different types of tissues. We've seen that the patient's size and their shape drastically influences the dose that they receive. And we know that dose is dependent on the energy spectrum, the X-ray fluence that's heading towards the patient. And as X-rays pass through a patient, the lower energy X-rays are preferentially attenuated by the photoelectric effect, and we get a harder beam or a higher average energy of that X-ray beam as it passes through patients. So that then becomes difficult to assess what type of dose is happening through the patient. We know that the rotation of the X-ray source around the patients mean that if we were looking at a specific spot on the patient and we say, what dose is that specific tissue getting? Well, it depends where the X-ray source is at that given point in time. And lastly, direct measurements of absorbed dose is just completely impractical. We can't place dosimeters within the tissues of the patient and measure directly the ionization that's occurring. That just can't happen. when we're measuring absorbed dose, we're measuring energy deposition and not risk. If we want to try and tell a patient how much risk they have from a specific examination, we need to account for more factors than absorbed dose can allow us to. We need to look at the type of radiation as well as the tissue sensitivity. These two factors are going to determine the risk to the patient much more than the absorbed dose alone. And I'm going to show you how we can take the absorbed dose and account for these factors to get a risk estimate later on. So let's take the absorbed dose and account for the type of radiation. This is what's known as the equivalent dose. We call the equivalent dose H to the subscript T tissue here. We take the absorbed dose and we apply what's known as a weighting factor, a radiation weighting factor. Now, when we looked at linear energy transfer, we said that X-rays have a much lower linear energy transfer than, say, something like an alpha particle, which is a heavier, more highly charged particle. Now, the weighting factor for X-rays and gamma rays is actually 1. So when we convert our absorbed dose to an equivalent dose, the numerical value is going to stay the same. The only thing that's going to change is our units here. Our weighting factor is millisieverts per milligray. So this gray is going to cancel out with our absorbed dose gray. We're going to leave ourselves with an equivalent dose that's measured in millisieverts. Now, what we're saying here is that for the same absorbed dose between X-rays and alpha particles, the same joules per kilogram deposited into the tissues, that patient is 20 times more likely to get long-term, say, cancer or stochastic effects from an alpha particle than they are for the same absorbed dose of X-rays here. So the equivalent dose accounts for the type of radiation. It's often forgotten about in X-ray radiation because this weighting factor is 1. But importantly, those units change because we're now talking about risk. Again, this has said nothing about the patient yet. So our equivalent dose hasn't taken the patient into account. It's taken into account the parameters that we've used, say, in our CT machine, and the type of radiation that we're using to calculate some form of risk. What we want to do now is try and calculate what risk comes from the specific tissue type. Different tissues have different propensities to develop long-term effects, such as cancer. And what the International Commission of the Radiological Protection have done has created tissue weighting factors. Weighting factors that say how much each of these tissues contribute to the total cancer coming from radiation. And these figures, 1, you'll see that they're all quite similar to one another, and 2, they've changed many times over the years. So that should ring alarm bells here that these are just estimates. They're more ballpark figures trying to get us in the right regions of the tissue weighting factors. They're not very, very specific. But they show you the differences between the tissues. Tissues that have a higher cell turnover are more likely to develop cancers long term. Slow growing or tissues that don't replace very often, like brain tissue, have much lower weighting factors. And what they've done is they've looked at, say, the atomic bomb survivors who were exposed to whole body radiation, and they've looked at which tissues go on then to develop cancer. They've looked at patients who've had long-term radiotherapy, medical radiation, and seen the propensity for each of these tissues to develop cancer. And they've created a whole body risk for these tissues. So all of these are going to add up to 1 in total. And what we do is for a specific examination, say an abdominal CT, we take each and every organ that's exposed to radiation in that abdominal CT. So say we take the stomach. We calculate the absorbed dose. Again, we've got an issue there because it's quite hard to calculate absorbed dose. So we need a way of estimating that. And we multiply it by the tissue weighting factor. We do that for all of the organs in that specific examination, and we add up each one of those values to give ourselves an effective dose. That means for a specific CT examination, we're going to get a total effective dose. Now, the effective dose attempts to determine what dose exposure to the whole body would give the same stochastic risk as this specific examination that we've taken here. Now, this is all good and well in theory, but again, we have no way of accurately measuring absorbed or equivalent dose in CT imaging. So what we need to do is have ways of estimating dose in CT imaging. And that's what we're going to look at next. How can we take a specific CT examination and estimate the dose that that patient received? And how can we account for the different shapes of patient that we have, the different parameters that we use in our CT machine, the different lengths of scans that we're going to use? All of those we're going to look at in our next talk, where we look at CTDI, DLP, and ultimately calculating an effective dose for a specific CT examination. So I'll see you all in that talk. Until then, goodbye, everybody.